In this video, I'll be introducing path homotopy and some properties of path homotopy. So first of all, what is path homotopy? So this is going to be highly related to normal homotopy, just with one added condition. So first of all, what is a path? A path is, I'm going to notate it as f, and it's going to go from x0, a little squiggly line, until x1. You'll probably not see this notation anywhere else. It's just easy to write out, so that's what I'll use for notation. And what this means is it's going to be a function that takes you from the closed interval from 0 to 1, which is also called I, and it'll take you into some topological space x. And it has the added condition that f of 0 is x0 and f of 1 is x1. And so this is really just a path between the two endpoints x0 and x1. Alright, now what is path homotopy? Well, let's go ahead and pick two endpoints, say x0 and x1. Then we will have two paths between them, say f and g. What is a path homotopy between f and g? Well, a path homotopy will be a continuous transformation between them. So this one will continuously morph over time into g while preserving the endpoints. So x0 will not move. x1 will not move throughout the entire homotopy. And that's the difference with normal homotopy, where the endpoints don't have to be preserved, and it's not even with the structure of having endpoints most of the time. Now let's go ahead and see an animation that presents this. So right here we have the two paths. The green one, f, on the top is going to be the start. The red one, g, on the bottom is going to be the end. It's going to transform from the green one to the red one. These two endpoints, these two black points, are the endpoints, and they will stay still during the entire transformation. Let's go ahead and see the homotopy. And you can see it slowly morphs one over time into the other while preserving the two endpoints. Those endpoints never move throughout the entire thing, but the curve morphs over time from one to the other. Alright, now that you understand what path homotopy is, let's go ahead and give a formal definition. So what path homotopy is it's going to be just like normal homotopy, except on paths where it preserves the two endpoints. So let's say we have two paths, f and g, which both go from x0 until x1, and this is in some topological space x. Then a path homotopy between them is going to be some function h, and this is going to be a continuous function. Now the interval from 0 to 1 is now going to be called I, so it'll take you from I. This is replacing the domain of the function because that's the domain of each of these two paths, and then cross I. So this first input will represent the input on the paths, and the second input represents the input of time, for the time of the transformation. And now it will take that into the topological space x, and I'll go ahead and represent this as h of s comma t. So s will be the first input, t will be the second input. Now this has to have a couple properties. So the first two are just going to be the ones from normal homotopy, which is that h of s0 is going to be equal to f of s, and that h of s1 is going to be g of s. So basically it starts at f of s, transforms into g of s. But remember, we have to preserve the two endpoints throughout this entire transformation. So what that means is that h of 0 and then t, so for any time input at 0, and it has to be x0, or the first endpoint. And then h of 1t, or throughout any time frame, the value at 1 has to be x1. Now these two just mean that throughout the entire transformation, anytime t, these two endpoints will be preserved. Now, I will represent path homotopy by a congruence with a little p. And I'll represent path homotopy classes with the brackets just normally. Alright, so these just normal brackets will represent path homotopy classes as well. And it just depends on the context in which I use them that will determine whether it's homotopy or path homotopy. Now note that this relation has all of the same properties as normal homotopy. It's going to be reflexive, transitive, and symmetric. So this is still an equivalent relation, and thus these are equivalence classes. It has all those same properties of homotopy while only having two added conditions. Let's go ahead and look at an example, namely the example of convex sets. So first of all, what is a convex set? So a convex set is going to be a subset of some Rn such that any 2 points can be joined by a line contained in A. What does this mean? Well, let's go ahead and look at an example. Let's say this is the set A, and we have any 2 points in A. They can be joined by a line, and this line exists entirely within A. So let's go ahead and look at that one. And of course, by line, I actually mean line segment. Alright, let's go ahead and look at an example that isn't convex, namely something that looks like this. Now, you would correctly identify that this is concave, but the real reason is because if I have a point here and a point here, try to draw a line between them, right here in this section, it's no longer in that set. So this is not convex. Now, the importance of convex sets in terms of homotopy is namely the line homotopy. So let's go ahead and say we have two paths, f and g, which is between x0 and x1 in some convex set A. Then I can create a general homotopy between any two paths, h of st. And this is going to be equal to 1 minus t times f of s plus t times g of s. This is going to be called the line homotopy. Now what this is going to look like is you have your convex set, you have your two endpoints, x0, x1, you have your two functions, or two paths going between them, and then between any two of the points at the same point s, so this is going to be f of s right there, and this one right here is going to be g of s, then you go ahead and draw a line between them. You draw the line between them, which is guaranteed to be in the set by the fact it's convex. And then throughout the time t, you just slowly move along this line until you end at g of s. So you go from f of s, move along the line to g of s. Let's go ahead and see this with an animation. So right here, we have a diagram. This outer ellipse is going to be the convex set A. This is the topological space we are in. This top curve, this green one, is going to be the starting curve. This bottom one, the red one, is going to be the ending curve. These two black dots at the end are the endpoints. And then all of these lines are the lines from which the points will travel along in the line homotopy in this convex set. Let's go ahead and see what that looks like. You can see those three blue points move from the top one to the bottom one along those lines. And that's going to be for every single point in this homotopy. It's just moving along those lines in that way. So hopefully that helped you understand what this line homotopy is. And this is the general formula, and you can easily prove that this is continuous by it being a product of continuous functions. Now, we're going to define a notion that is going to be very important involving paths, namely path products. So we define products on two different types of paths. You have f, which is going to be from x0 to x1, and then you have g, which will be from x1 to x2. So these are two separate paths. what you can then do is define a new path, which is going to be called f star g, which will be from x0 to x2. Let's go ahead and draw this out. So right here, you have the two paths f and g, and now f star g is going to be like ignoring this middle point and just viewing this as a whole. So this is going to be what f star g is going to be. It's just going to be skipping over that middle point and then speeding it up so that it has the correct time unit. Now, how do I rigorously define that? Well, let's go ahead and do f star g of s. The way we define it is, well, it's going to be defined in a very similar way to the transitive homotopy that we discussed last time. Namely, it's going to be f of 2s for s between 0 and a half, and it's going to be g of 2s minus 1 for s between 1/2 and 1. Now, it's very easy to check that this is continuous by the pasting lemma. So, right there, we have the notion of a product. This is going to be algebra. This product definition is going to be our introduction to the actual algebra of within topology. Now, we're actually going to be looking at this product on equivalence classes. This is going to be very important because this will have a lot of properties with equivalence classes that it wouldn't have on just normal functions. All right, but how do we define this? Because these are different objects from what the store operator was defined on. Well, it's going to be just the equivalence class of f star g. So equivalence class of f star equivalence class of g is just equivalence class of f star g. That makes plenty of sense. How do I know that this is well defined? Meaning, if I were to take a different representative from this equivalence class, because remember, you can take any number of representatives, because this is a set of different functions, where this equivalence class will be equal, but the two functions are not equal, and we go ahead and product that with a different representative for this equivalence class. And remember that for these to be equal to each other, they just have to be homotopic. So you have these two different representatives, and then you use the definition of this product to get f prime star g prime. Is this equal to f star g, the equivalence class? So let's go ahead and say we have an equivalence class, let's call it f, which is going to be from f, it's going to be a path homotopy to f prime. Because remember, if these are in the same equivalence class, that means that they are path homotopic. And then similarly, we can have a homotopy g, which is going to be from g to g prime. This path homotopy g. Then what I'll do is define a new h, which will be a path homotopy from f star g to f prime star g prime. And the way we define it is going to be very similar to the transitive homotopy again. And the way we define it is h of st is going to be equal to f of 2s comma t for s between 0 and a half, and g of 2s minus 1 t for s between 1/2 and 1. Now you can go ahead and check that it satisfies all of the properties of path homotopy. It's very easy to check that. And so what you get is that we have a new path homotopy between f star g and f prime star g prime. Therefore, these two homotopy classes are going to be equal to each other because their representatives are homotopic, or path homotopic. Now, I'm going to prove a general lemma. I'll call it lemma 1. Now, this will be proving it for normal homotopy, but you can almost immediately show that it's also true for path homotopy. The lemma states that if I have f and f prime, which is from x to y, and I have g and g prime, which is from y to z, and I also have it that f is homotopic to f prime, and that g is homotopic to g prime, then that means that g composed f is homotopic to G prime composed F prime. Now, how do I go about proving this? Well, let's go ahead and say F is the homotopy between F and F prime, and G is the homotopy between G and G prime. Then I can go ahead and define a new homotopy H, which will be between G composed F and G prime composed F prime. And I'll go ahead and define it as H of xt is equal to, well, let's go ahead and think about what this is. So this composition will be a function from x to z. Basically meaning we want to end up in z. So what function do we know already ends up in z? Well, g does, because g is a homotopy between g and g prime. And so I think we should just do g first. Alright, now g has two inputs, x and t. What should this x be? Because this x will come from y. Because, again, g is a homotopy from g to g prime. So this x value comes from the domain of the functions, which is y. Well, there is actually a function that ends in y. Namely, this homotopy, capital F. That ends in y because it's a homotopy between f and f prime. And so instead of having x, we should really have f. Because f will end up in y, which is what you need for this first input. Alright, now what should the inputs of f be? Well, this x is again coming from this first set x, capital X. And now f, as a homotopy, will have its first input also be from this capital X domain. And so therefore I can just do f of little x right there. And then I can just do t again. So this t will just be plugged in normally into both homotopies. And then this will be the homotopy between them. And that's very easy to check that that is a homotopy between them. So if you trust me that that is a homotopy between them, which it's very easy to prove so, then that's the proof. Alright, now this lemma is actually related pretty heavily to another one, which I'll write over here. Alright, this is going to be lemma 2. And lemma 2 basically says that k composed f star g is going to be equal to k composed f star k composed g. Basically meaning, given composition, you can just distribute that function you're composing it with this product. So this product is distributive with composition. Now this is actually really easy to prove, because what is k composed f star g of s? Well, it's going to be from the definition of f star g. Well, f star g is f of 2s, for s between 0 and a half, and g of 2s minus 1 for s between 1/2 and 1. And then, because we're composing it with k, you just do k of both of those things. Now what you can very clearly see is that this is going to be equal to the same thing as if I would have just done k composed f star k composed g applied to s. Because each one of these is just k composed f of 2s and k composed g of 2s minus 1. And then by the definition, that aligns. And so that's that theorem, that's that lemma proven. So those are our two theorems about homotopy and composition. Now let's go ahead and move on to the main theorem of this video, which is going to be very cool and very important. So the theorem that I'll be proving, which is going to be the most important theorem of this video, is going to be the properties of the product. Namely, that it has an identity. So this identity will be a map, EX naught, which will take you from the interval into the topological space X, and it'll send every single value A to just this X naught. So this X, it's a constant function where its value is always this subscript. Alright, now the theorem says that if I have a path which is from X naught to X1, then we will have it that EX naught star the equivalence class on F, the equivalence class on EX naught star the equivalence class on F is just going to be the equivalence class on F, and that the equivalence class on F star the equivalence class on EX1 will just be equal to the equivalence class on F. So it's a two-sided identity. This will be accompanied by inverses. So we go ahead and define a new function, f bar, which its value at s is going to be f of 1 minus s. F of 1 minus s. So that will be the reverse. If this is our path, f, its inverse path will just be flipping the direction on it to go the other way. What this theorem says, this theorem of inverse, is that the equivalence class on f bar star the equivalence class on f is just going to be the equivalence class on this identity EX1. So this is an inverse because when you product them together, you get the identity. And then it's two-sided. So equivalence class on f star the equivalence class on f bar is going to be equal to EX naught. Alright, then 3 is going to be that of associativity. So this one is very important. What it says is that if I have in parentheses f star g, and then I take that product, and then I star it with the equivalence class on h, then this will be equal to, if I were to rearrange the parentheses so that it would be f and then star the quantity of equivalence class on g star the equivalence class on h. Basically meaning parentheses don't really matter. That's what associativity means. You may correctly identify these as the 3 axioms for a group, and that's going to be correct. Because using these facts, we will turn this product operation into a group operation using what's called the fundamental group. But that'll be right at the end of this video. Let's go ahead and try and prove this first point, the identity. Now the way I'll prove it is by using what is called the identity curve, or the identity path, which will be a function from the interval to itself, which just sends, it's the identity on the interval. Now a way to look at this identity function is as a path from 0 to 1, because it starts at 0, ends at 1. Alright, then we can go ahead and look at the constant function E0. Now this will be a path from 0 to 0, right? Oh, look at that! This is from 0 to 0, this is from 0 to 1, therefore I can do E0 star I. And this will be a path which is from 0 to 1. So this path, which is from 0 to 1, what you should note is that I is convex. So using what we talked about before, that I is convex basically means any two paths between the same 2 points are path homotopic. So right here we have a path which is from 0 to 1, and right here we have a path which is from 0 to 1, which tells us that they are path homotopic. So E0 star I is path homotopic to just I. Now using lemma 1, which was that this homotopy is preserved through composition, and note that it's also true for path homotopy. If we take this path f, we can go ahead and compose it on both sides. So f of composed E0 star I is going to be path homotopic to f composed I. So right in here, using lemma 2, I can go ahead and separate it into f composed E0 star f composed I, which is going to be equal to, well, f composed E0. E0 is a constant function, so this is always going to be 0, meaning what comes out the other end is going to be a constant function, E at f of 0, which is now f of 0, because it's a path from x0 to x1, is just going to be x0, or x0. Then on the other side of this is f composed the identity function, which is just f. Now on this side, we'll also just have f composed the identity function. So we get that it's path homotopic to just f. Because f composed the identity function is just f. So you get e x0 star f is path homotopic to f, which therefore means that the equivalence classes are equal to each other. And then you can do the same exact thing, but instead of using E0, you can use E1 and then just flip it, and then you'll get to the other part of this theorem. Alright, so now how do I prove the second part of this, which is inverses? Well, the thing we look at is I bar. So taking this inverse and then reversing it. This is going to be a path from 1 to 0, I bar. Now what that means is that because I is then a path from 0 to 1, I can go ahead and product these. I can do I star I bar or I bar star I. It works either way. But I'll just be looking at I star I bar for simplicity. Now let's go ahead and write out what I bar is. I bar will be applied to some s, will be equal to I of 1 minus s. That is from the definition of the function bar. Now, this is the identity function, so it's just 1 minus s. Alright, that's going to be important. What is I star I bar? Well, I star I bar is going to be a path. It's going to be a path which is from 0 to 0. Another thing that's a path from 0 to 0 is E0, the constant 0 function. Again, I is convex, meaning that these two things are path homotopic. Now what does that mean? By lemma 1, or an extension of lemma 1, I can go ahead and do f composed on either side. Now by lemma 2, this is going to be equal to f composed I star f composed I bar. That's going to be path homotopic 2. By the same logic, this is going to be e at x0, the constant x0 function. F composed the identity is just f. Now what about the reverse of the identity? Let's go ahead and look at what f composed I bar applied to s will be. Well, it's going to be f of I bar of s, which is then going to be equal to f of, right here we have I bar of s is equal to 1 minus s, so this is f of 1 minus s, which by the definition of f bar is just going to be f bar of s. And so f composed I bar is just going to be f bar. So f star f bar is path homotopic to ex0, which is exactly what the theorem required, because then the equivalence class products are just going to be equal to each other. Alright, let's go ahead and prove number 3. Now this one I'm going to go all the way through it. It's actually very easy, it just uses some basic principles, but I'll go all the way through it just to be safe. Let's first calculate, without the classes, what f star g star h is going to be. So what this is going to be equal to is, well, by the definition of the product, it's going to be f star g applied to 2s, for s between 0 and a half, and then just h of 2s minus 1 for s between 1/2 and 1. this is going to be equal to, expanding out f star g, f of 2, now the input is actually 2s, so 2 times 2s is going to be 4s. So f of 4s, well, the input again is going to be 2s, so 2s is going to need to be between 0 and a half, which is the same thing as saying that s needs to be between 0 and a quarter. Then we will have g of, well, it's going to be double, and then its input is going to be 2s, and then that minus 1. 2 times 2s is just going to be 4s. So this is g of 4s minus 1. This is for 2s as its input between 1/2 and 1, which is the same thing as saying that s is between a quarter and a half. And then this h value stays the same. H of 2s minus 1 for s between 1/2 and 1. Now let's go ahead and look at what f star in quantity g star h is going to be applied to s. Well, it's going to be, by the definition, f of 2s for s between 0 and a half, and then g star h of 2s minus 1 for s between 1/2 and 1. What is this going to be equal to? Well, this is going to be equal to, well, f of 2s stays the same. It's going to be between 0 and a half. Then we split up the g star h. So this is going to be g of 2 times its input, which is 2s minus 1. All right. If you distribute that, you get 4s minus 2, g of 4s minus 2. And that is for its input, which is 2s minus 1 between 0 and a half. This is the same thing as saying that s is between 1/2 and 3/4. You can go ahead and check that that's true. Then we have h of 2 times its input, which is 2s minus 1, and then minus 1. You distribute that, you get 4s minus 2, minus 1, which is just 4s minus 3. And that's going to be for 2s minus 1 between 1/2 and 1. This is its input. That's the value from the definition. This is equivalent to saying that s is between 3/4 and 1. And so we get these two different functions, and we need to create a homotopy between them. So let's go ahead and define a homotopy h of st, which will act as a transformation between them. Alright, you can see that they're mostly in the same order. What changes is the coefficients and what you're subtracting from s. So f, where do we want it to start? Well, we want it to start with this one, which is going to be 4s. Now, where do we want it to end? We want it to end here, which is at 2s. So the way to do that is going to be 4 minus 2t times s. Because if I plug in t equals 0, I get f of 4s. If I plug in t equals 1, I get f of 4 minus 2, which is going to be 2s. So we start at f of 4s, we end up at f of 2s. And this is going to be for s between 0 until 1 over 4 minus 2t. It's because we want to go from 1/4 from this first one to 1/2 in the second one. And so you start at 4 on the bottom, you go until 2 on the bottom. Alright, so then for g, we want to start with 4s minus 1 and go until 4s minus 2. That's going to be easy. It's going to be g of 4s minus 1 plus t. Alright, because if you plug in t equals 0, that's 1, that's where we start. You plug in t equals 1, that's going to be 2, which is where you end with that minus, and it's 4s for both of them. So that's for s between, well, 1 over 4 minus 2t, because again, that's going from 1/4 until 1/2, and then we also want to go from 1/2 until 3/4. So how do I do that? Well, the way we do it is just by 2 plus t over 4. That's because if you plug in t equals 0, you get 2 over 4, which is a half. If you plug in t equals 1, you get 3 over 4, which is 3 over 4. And then for h, the way we do it, we want to start off with 2s minus 1, end up at 4s minus 3. So that's going to be 2 plus 2t, if we're going between 2 and 4, times s, and then minus, going between 1 and 3, it'll be 1 plus 2t. That'll be for s between 2 plus t over 4 until 1. So this is a very complicated piecewise function. What you can check is that it actually satisfies as a homotopy between f star quantity g star h and quantity f star g star h. And the reason why it is because we actually just designed it so it will start so that all of the functions align, and then it'll end where all these parts of the piecewise function align. And so this was just a needlessly complicated way of showing the homotopy specifically between these two things. And a much more general theorem is that if I go ahead and do f0 star f1 star all the way up until fn, the parentheses don't matter. So if I do any sort of parentheses in here, because it's associative, this will just always be the same value. And of course, I actually meant among the equivalence classes. And so, because these two maps are homotopic, that means they're equivalence classes.
Or f star equivalence class of g star the equivalence class of h is going to be equal to, parentheses, equivalence class of f star the equivalence class of g, and then that star the equivalence class of h.
And therefore, we proved associativity and inverse and identity using all of this work. And like I said when I first introduced the theorem, this will be used to create a fundamental group. Alright, I'll get into this fundamental group more next time, but hopefully this was a good introduction to the product. Anyway,